Hello everyone, this is Dr. Hopkins narrating the next in our series of videos for 472. And today's video is related to the kinetics of photophysics and a little bit of a mention of photochemistry. So first off, photochemistry, basically that's using photons as reactants or products. So we'd have maybe a ground state structure, we excite it with a photon, we get an excited state structure, so some change in the electronic structure, and then it rearranges into products. Okay, so that would be a case of photochemistry. Each one of these steps would have a kinetics process. Let's focus more on the photophysics because in the end we're going to get to something that we want to discuss in this class. And let's do a kinetic analysis of this. So the first step in any process where we're using photons is we have to have some excitation. So we have to go from ground state to excited state. And in this case, these processes are fast because electronic rearrangement or electronic motion is very fast. And so you get rate constants that are on the order of 10 to the 15, 10 to the 18. So in other words, each individual event is taking femtoseconds to attoseconds. So they're very rapid. And then once you're in the excited state, we have, like I said, have electronic rearrangement. If we were talking about straight organics, it could be a triplet spin state or a singlet spin state. So in other words, either paired electrons in the singlet or unpaired electrons in the triplet. But the thing about excited states is that they won't last forever. They have a finite amount of time. The molecule will only spend a finite amount of time before it finds its way back to ground. And so let's discuss some of the pathways, the kinetic pathways to get to the ground state. So the first thing we're going to discuss are non-radiative pathways. So those that are not emitting these visible or UV photons, the photons that amount to the electronic excitations, de-excitations. And the first one is just generally non-radiative decay, going from excited to ground. We give it a rate constant, a non-radiative decay rate constant. This is like if the molecule vibrates its way back down to, it kind of vibrates, releases heat, and gets to the ground state. Another possible way to get to the ground state is through energy transfer or another collision. So we have excited state A, we have ground state A. If they run into each other, we just exchange the energy. We'll explore this with not where they're not the same molecule later on in the video. So what about radiative decay pathways? Well, the first one we're going to think about is fluorescence. So we're in the excited state, and then it emits a photon that bridges to the ground state. And in this case, so fluorescence generally means that there's no spin change. So if we're just standard organics, that means singlet excited state to singlet ground state. The other thing that it can do is in the excited state, it can cross over from a singlet state to, say, a triplet state, if we're talking about organics, and that's intersystem crossing. But in other words, what we have is a spin change, but we're not going to ground state. And then once it's crossed over into that triplet state, the triplet state then phosphoresces, emits a photon, and it changes its spin from the excited state to the ground state from a triplet to a singlet. And so it'll emit a photon. So we look at these in terms of kinetics. This is KF. The fluorescence rate constant is typically on the order of 10 to the 9. So another fluorescent, the time that it takes for photons to go from excited to ground state is nanoseconds typically. Intersystem crossing can be anywhere from 10 to the 9 to 10 to the 6. This will depend on the molecule, of course. And then the triplet, the phosphorescence decay, so once again, this should be a P, can be anywhere from 10 to the 6th to 10 to the 1st. So that means that it may take microseconds or it could take seconds in a phosphorescence. So phosphorescents are very long life, a long time, and they spend a long time in the excited state, whereas a fluorescence, they spend a shorter amount of time in the excited state. And then, of course, if we fold in from the previous slide, the non-radiative and energy transfer, they depend on the details of the structure, physical properties like temperature, etc., concentrations. So let's look at this in terms of the analysis. Let's set them up all as elementary reactions. So we're going to look at this excited state because that's kind of the linchpin of all of this. And so the excitation depends on the light intensity. So we just put intensity of excitation. So however many photons we're pumping in will be however many excited state molecules we'll get. And then once in the excited state, of course, they can fluoresce. And so this rate constant, let's think about this as a first order rate constant in terms of the excited state. It can non-radiatively decay, once again, a first order rate constant. An intersystem crossing, which is, once again, a first order rate constant, doesn't depend on any kind of collisions or so forth. What I don't have in there is energy transfer, which would be a second order rate constant or a second order elementary step. So if we look at the rate of appearance of our excited state, it depends on the intensity of the excitation, and then these are all of the pathways down to the ground state. So that's a negative of this. If we consider the fact that the initial zero, the A star zero concentration, initial concentration, is strictly related to the number of photons we're pumping in. It's not related to anything changing in terms of our ground state. Our ground state population is large, so our excited state population is just related to this excitation. And we set this K as the sum of all of these rate constants that decay the excited state to the ground. We can measure this by this rate constant, this rate of decay, the rate of appearance of the excited state A, in terms of by looking at its fluorescence lifetime tau. And now a tau is basically just the inverse of the rate constant, and it's an amount of time that the excited state molecule spends in that particular excited state. And it's inversely dependent upon these radiative decay, or excuse me, these decay rate constants. We're also going to define a quantum yield, okay, and which is basically number of events depending on what we're talking about. So it could be the fluorescence quantum yield. So in other words, if it's fluorescence quantum yield, this is the number of photons fluoresced over the number of photons absorbed. So the largest you can get is 1. If you got one fluorescent photon for every one absorption photon, you'd have 100% quantum yield, or a quantum yield of 1. If we sum all of the the decay pathways, they all will sum to 1. So our fluorescence quantum yield, like we're talking about here, is this KFA, because we had that from the previous slide, over the number of photons that are exciting our ground state population. It's not real easy to determine this number of photons, and then we're going to assume that this A star is basically small but steady. So we just have constant excitation of light. We're just constantly pumping up, and we always have this constant, excited state population. Then our quantum yield, fluorescence quantum yield, is related to the fluorescence divided by the decay constants. And so then we can remove these because they're constant, and they're divide out because they don't change, and then we end up with this ratio of Kf to the over all of the Ks. So our lifetime is the quantum yield over the fluorescence rate constant. Okay, so if we can determine our lifetime and our fluorescence rate constant, we can know the quantum yield of our system. All right, so let's take a case where we add in something that can interact with our molecule, so fluorescence quenching. So that lifetime, if there's nothing there, that lifetime is kind of constant. If we hold everything else constant, that's unique to that system. And so these fluorescence lifetimes can be used to measure any kind of intermolecular interactions of the excited state molecule with another molecule. So if we consider that we start with excited state A, we add in this quencher Q, they interact, they exchange the energy, and the quencher takes the energy and then decays to the ground state. Okay, so we're undergoing an energy transfer. So if this step this initial energy transfer step is elementary. So we have minus the decay, the rate of disappearance of the excited state is, we're going to have, and I don't show it, but this is also fluorescing. So there's a fluorescence rate, and then there's a KQ, which is a bimolecular rate constant of how often, or related to the interaction of the energy transfer between A star and Q. And so we can substitute this in. And typically we would want to compare quenched versus unquenched. So if we had our emitter with quencher and an emitter without quencher, and we compare those, we can put it in form of the Stern-Volmer equation and typically determine it by plotting. So the quantum yield, the fluorescence quantum yield unquenched over the quenched quantum yield is equal to 1 plus the unquenched lifetime times KQQ. Okay, Q is our concentration of the quencher. It's not often easy to measure the quantum yield of a measurement, but you can determine intensities. We just, we run an emission spectrum and fit the area under the curve. And so the intensity of fluorescence unquenched over the intensity of fluorescence quenched is equal to 1 plus, this is KQ over KF, times the concentration of Q. 0 indicating our unquenched like that. So if we plot this, IF0 over IF versus Q, we can determine our rate constant of interaction and our rate constant of the fluorescence. So in quenching, when we're talking about this intermolecular interaction, this KQ is just the empirical measure of the efficiency of that intermolecular interaction. But let's look at a few mechanisms of excited state quenching. So first, you have collisional deactivation. So if we just have molecules bouncing around in space, say a gas phase, and they run into each other with enough energy, they'll transfer the energy, kind of like billiard balls. The second possible mechanism, or another possible mechanism, is electron transfer. So you might get two molecules come together. The excited state transfers an electron. So you actually do an oxidation reduction process in the excited state that you almost inject an excited electron into the quencher, and that changes, that amounts to an energy transfer process. But the most interesting for our purposes is this resonance energy transfer. And that's where you have the energy donor and energy acceptor are basically exchanging photons, or exchanging a photon. And so in order to do that, we have to have overlap between the excited states. So in other words, we have to have overlap of the absorption of the acceptor and the emission spectra of the donor, of the donor molecule, the excited state molecule. And the energy transfer efficiency is related to this, once again, quenched versus unquenched intensities. Now we can apply, what we're talking about. There are a couple of different theories with respect to resonance energy transfer. We're going to specifically rely on first order theory, okay, where we have a dipole-dipole interaction, and basically it states the efficiency of that energy transfer is related to the distance, and actually to some extent to the orientation between the donor and acceptor. So shorter distance, closer they are, the more efficient the energy transfer is in a Forster mechanism. And in 2, we're basically describing the energy transfer as a photon emitted by the donor and absorbed by the acceptor. Now, it doesn't have to be a real photon. It could be a virtual photon. It's just an exchange of that radiative electromagnetic energy between the two two molecules. And so that efficiency is related. It's a 6th order distance dependence. So it scales to the power of 6, so it falls off quite rapidly at long distances. And you have, this is the expression. R0 is an experimental measure. It's something you can't really calculate. You might be able to calculate it, but it's most often experimentally determined for any particular donor acceptor where the efficiency is 50%. So at what distance is the half of the photons being transferred from the donor to the acceptor? That's your R0, and that depends on your donor acceptor pair. So whatever combination of dyes you're using, that sets your R0. And then R is your experimentally determined value. So if you determine the efficiency, you can determine R, and you can measure how far apart those dyes are up to about 9 nanometers, depending on which sets of dyes, or fret dyes, if you will. And this is a common technique that's used to determine distances in biological systems and even dynamics in biological systems. So we'll hear more about that later.